Okay, all right. So, welcome back. So I rewrote here the Hamiltonian for the JC model. So this is our harmonic oscillator, our two-level system, our qubit, and over here, this term over here, this is the interaction that we got before.
Can you just repeat omega fs? I didn't get a chance to write it down.
Can I? Sorry?
Just write again the expression for omega fs.
For, oh, omega naught. Yeah, omega naught.
Yeah, omega naught.
Yeah. And omega naught, yeah, here. So omega naught, that was, hang on. Yeah. Where is it? It was d epsilon naught star dot epsilon c, right? So we have to have this, have to have that, and there's a factor of 2, and there's an h bar. Do I have it all correct? Yeah. Okay, so this is the Rabi frequency. But as you will see in just a moment, it really doesn't matter that much, okay? Because your system will have some omega naught, the vacuum Rabi frequency, and basically the scales, these are the scales, omega cavity, omega q, and omega naught. These are the scales that define the problem itself. So now what we're going to do is we're going to look at this model. We're going to look at the energy levels at the spectrum and the dynamics on resonance. On resonance means omega c very, very close to omega q. Very, very, very close. And omega c very, very far, which is called the dispersive regime. Okay. Of course, when I say very close or very far, it's with respect to our only other time scale, which is the Rabi, the vacuum Rabi frequency. So we're going to start on resonance. So on resonance. So what I'm going to draw right now is first is the uncoupled system. So suppose that we have no interaction. We're just going to have a harmonic oscillator and a qubit. So for each level of the qubit, there's going to be a whole spectrum of harmonic oscillator, right? There's going to be a harmonic oscillator with sigma z in -1 and harmonic oscillator with sigma z in +1. Okay, so if the y-axis that I'm drawing here, this is going to be the excitation number. So the number of excitations in the system. So you can have 0, 1, 2, 3, and so on and so on. And so we're going to have these energy levels over here. I'm going to label them. And then you're going to see what they correspond to. So this one is going to be 0 photons and the qubit in the ground state. Just to disambiguate the 0 and 1 of the qubit, I'm going to label them as ground and excited. So G and E are going to be the labels for the atom. So here is going to be 1 photon in the cavity and qubit in the ground state. 2 photons in the cavity and qubit in the ground state. 3 qubit in the ground state, and so on and so on. So the energy difference between these two levels here, this is h bar omega c. H bar omega c. Now, this ladder corresponds to the harmonic oscillator, only the qubit being in the excited state. So this is 0 photons in the cavity, but the qubit is in the excited state. Okay, so this is omega q, and then this is 1 photon in the cavity and the qubit in the excited state, 2 photons in the cavity, the qubit in the excited state, and so on and so on. So this is the uncoupled system. Now what is happening is that we're going to be adding this coupling term over here. And what this coupling term is going to do, it's going to create a splitting. These two things are on resonance, and they're going to be split, and you can already guess at what frequency they're going to be split. The Rabi frequency, right? This is very similar, and as I go through this on resonance description of this Hamiltonian, you're going to see that it is very similar to our classical spin being driven by a classical field. You're going to see the similarities there, okay? And you're going to see the differences. So when we now add the interaction, what happens is these two levels are going to interact and split. So now instead of two degenerate levels, you're going to have two levels, and these levels are going to be separated by square root 1 of omega naught. These two levels over here are going to be separated by square root 2 of omega naught. And these two levels here are going to be separated by square root 3 of omega naught. Okay, so with no coupling, you can see that the n plus 1 G and NE levels are degenerate. So n plus 1 G and NE are degenerate. And 0G, this is the vacuum. There are no photons in the cavity. The atom is in the ground state. There is nothing but vacuum, basically. Okay, so you can call this the vacuum state. With coupling, we get these splittings over here, and they come about from this interaction term. Now, if you look at this whole Hamiltonian, you will immediately recognize that M, if this is the operator of the number of excitations. So I wrote this here on the scale of number of excitations, so you can see that basically what this Hamiltonian does, you can split it up into many Hamiltonians. And each Hamiltonian is a number conserving Hamiltonian. Because all this term does is it destroys one excitation and creates another, destroys one excitation and creates another. So if we have a defined n number of excitations in that system, it will stay in that subspace. Only we will have certain dynamics within that subspace. But there will be no movement between these subspaces. And you can see it by the fact that if we define an operator M, A dagger A, plus sigma plus sigma minus, you can see that M commutes with this Hamiltonian. Okay, so this is the number of excitations, and M commutes with our Hamiltonian. The second thing you can see is that if you're in a certain subspace, what happens is, and this is what we said at the end of the last lesson, is that the atom and the oscillator are going to be exchanging quanta. Now they're on resonance, so this is an energy conserving, a really energy conserving term right now, are going to be exchanging the quanta at a frequency, and this frequency is going to depend on the number of excitations. See, so omega naught, or square root 2 of omega naught, or square root 3 of omega naught. Okay, so so they're going to be exchanging the excitation backwards and forwards, and the splitting is basically going to be what is called the n photon Rabi frequency. Which you can define omega n as omega naught times square root of n plus 1.
Can you please explain again why do we consider the first point, n plus 1 and g, and n e as degenerate, because we only look as the number of excitations?
No, this is our, we're talking on resonance right now. So I defined omega q equals omega c.
Ah, okay.
So all I did is write the energy levels, but because this energy difference is this energy difference,
yeah, okay,
then they're equal.
And
they don't have to be perfectly equal. We're going to look now in the vicinity, so kind of equal. Okay, so we're not going to look exactly. We're going to look a little bit over there, and then afterwards we're going to look when they're pretty far away from each other. So then this ladder will look a little different.
And we also assume that there is no new degeneracy because of the splitting, because we assume that omega naught is far away from omega c.
We're assuming that omega naught is much smaller than omega q and omega c.
So there is no new degeneracy because of the splitting, right?
Exactly. This splitting is tiny with respect to this.
Okay, thanks.
Okay, so there is no interaction, and there are no other terms that can couple these levels. Yeah. Already, even though we took this approximation, already when you're drawing this out, just like you stated, if you go to omega naught being too big, you're asking yourself, am I still okay? But to begin with, we went to this model saying we're in this limit. Okay, so if you break away from this limit, you need to add the extra two terms and see what happens in the general case. Okay, so so this is what happens exactly on degeneracy. So you have these split Hamiltonians, and now what we're going to do is we're going to look at just the separate Hamiltonian for the doublet. So we're going to look at some Hn Hamiltonian that's just looking at one specific doublet. Okay? So this is what we're looking at now. And we're going to look at very small detunings around this resonance condition. So we're going to look at Hn, which is the Hamiltonian for a certain doublet near complete degeneracy. So the Hamiltonian for a certain doublet, like we saw, is going to be h bar omega c a dagger a plus h bar over 2 delta. Delta is our small detuning from resonance, sigma z, plus omega n sigma y. And maybe I'll define delta. So delta is basically omega c minus omega q. And we're assuming it's small right now. Okay, so we're looking near complete degeneracy. And then you can transform those sigma plus and sigma minuses into sigma y. And because of this slight detuning, you get this delta term. If you go back to what we did at the beginning of the previous lesson, it's exactly the same transformations. Okay, so you can get to this. And this is our interaction part, V. Well, let's call it Vn. Okay, because it depends on n, which doublet we're looking at. And if we look at Vn, so again, going through the interaction picture, get rid of this part. This is the important part. Okay, Vn. And now we can write Vn in matrix form. So we'll have delta and delta over here. Here we'll have I omega n and minus I omega n. And this we can diagonalize and solve. Okay. And if we diagonalize and solve, you already know the answer because you've seen this form already. Remember I told you, think about the classical magnetic moment interacting with the classical field. It's basically the same. Okay, sorry, the quantum spin interacting with the classical field. So the energy levels are just going to be h bar omega c n. This comes from that. That's really not that interesting, but you have h bar over 2 square root of delta squared plus omega n squared. And if you draw this out, so this is E, and this is delta, the detuning. Then these are the two solutions. And this is right on resonance. So this is right on resonance. And right on resonance, you have h bar omega n. And you have these two steady states. The plus and minus steady states. Okay? So these are the eigenenergies of this Hamiltonian, this doublet Hamiltonian, the eigenenergies plus and minus. So we're going to have plus n, n symbolizes which n we have, and minus n. So these are the two states of the doublets, and this is what it looks like in the close vicinity. And this looks exactly like our spin in classical magnetic field now. It's very resembling of that picture, just in terms of that energy. Okay. Now, these states over here, if you look at their character, before, when we had an uncoupled Hamiltonian, we had photons in the cavity, right? And we had excitations in the qubit, excited and ground. But now we have these new eigenenergies, and they've now they have a mixed character. Okay, they're no longer, you can't no longer think about them as a photon excitation or an atom excitation. These are now hybrid states. They're hybridized, and exactly in degeneracy they have 50% photon character and 50% atomic character, each of these states. Okay, so let me write this down. So each doublet one is a little bit like with the classical field, right? Classical two-level system, or sorry, it's a like two-level system in classical field. So it's a little bit like that. And the plus minus n states, if you write them in the original bases, these are just 1 over square root 2 n plus 1 g plus minus n e. And you can see that they're, let's call it 50% atom and a complete degeneracy. They're 50% atom and 50% photon. Now, since we have this solution, we can also solve for the time dynamics. So let me write the solution for the time dynamics. So we can solve for some psi of t for the dynamics of a certain doublet. And we know that we'll get some 1 over square root of 2 plus n e to the minus I omega n over 2 t plus minus n e to the I omega n over 2 t. So plus and minus these are our steady states, and they just pick up this phase at a rate omega n. But what is interesting is to look in the uncoupled bases, maybe. Let's give some insight. So this is in the coupled bases in plus minus. In the uncoupled bases, you can also solve for psi of t. And here I'm assuming that psi at 0 is E and some n. Okay, so we started with the atom being in E, and we have a defined number of photons in the cavity. So I'm starting with a state which is not plus or minus. If I start with a steady state, I will just stay there and pick up a phase. But now, I'm starting in a state which is essentially a superposition of these two. And you can look at the evolution of that, and if you calculate that, you will get cosine omega n over 2 t en plus sine omega n over 2 t g n plus 1. And now you can actually see the dynamics itself that we were talking about with the excitation being swapped from this state to that state between the doublet. Okay, so we have our doublet, and the excitation is doing Rabi oscillations between the two states of the doublet. And the frequency of the Rabi oscillations is just this omega n. But so notice that what is interesting here is that omega n increases as you go up to higher and higher doublets. So each doublet now is going to have a different frequency. The swapping rate between each doublet will have a different frequency. So if we look at the Rabi oscillations for each doublet, they will have higher and higher frequencies as they go up. Now, why is that interesting? Because that is where the whole thing kind of deviates from the classical behavior. So you can relate a single doublet to the classical behavior of being Rabi driven. But if now we go ahead and consider all the levels of the system, and let's suppose that we start with a coherent state. And this coherent state is going to occupy many, many n levels. Okay? Suppose that the atom can be in the ground state, and we start with a coherent state. And what's going to happen is we're going to have all these doublets rotating within themselves. So we're going to have a superpositions of many doublets which are rotating at many, many frequencies. And now if we look at this whole system, we can look at the atom itself, just the atom itself. The atom is going to be going from ground to excited, ground to excited, ground to excited, but according to all these spreads of the wave function. Okay, so what I'm going to do now is I'm going to pull up a PDF. Hang on, I'm going to do a share screen. Here's screen. This thing. Okay, can everybody see the screen? Yeah? Can someone say yes?
Yes.
Okay. So what I'm showing you now, this is page 156 from the Serge Haroche book, chapter 3, which I told you several times you should read. So go read. This is section 343. So above here, he's talking about what we talked about just now. You can see the equations that I wrote on the board. But here now, what we're considering is a coherent state. So suppose that we're starting with some coherent state. Okay. So where is he give? Does he give the coherent state? Yeah. Okay. So highlighted over here, this is the coherent state that it starts with. And suppose that the atom starts does he start here in the ground state or in the excited state? In the excited state. So the atom starts in the excited state. Okay, but it can also start in the ground state. It doesn't matter. And now you let the wave function evolve. And then you can see that each doublet here is evolving according to its different frequency. And what you're going to have is an interference of all these frequencies. You can calculate explicitly the probability of finding the atom in E. You have to evolve the wave function, and then you have to take out all the components that relate to E and add them up. And if you add these, this is what you get. So this is simulations. And And this is what we call collapse and revivals. Basically what happens is all these oscillations are interfering with each other, so you see these fast Rabi oscillations which are decaying, and it looks like dephasing, but after a while, can everybody see my mouse? Yes? Someone say
yes.
Yes. Okay.
Yes.
Yeah, okay. So you have these oscillations which decay very fast, but this is not regular decoherence because the information has not leaked out anywhere. So this is not the environment watching you. This is the information just going out and interfering in a coherent way inside the cavity, and then it comes back. So you're getting these revivals. And as you go to longer and longer frequency, it gets crazier and crazier, and it highly depends on what is your initial state. So here in the simulation, the cavity has a coherent state with average photon number of 15. Okay. So are there any questions about this and the dynamics? So this is really where you see the highly non-classical character of this interaction on resonance of the atom and the cavity. Okay, so do we have questions? All very clear? Okay, great. So the next thing that we're going to do, so this was a little bit about the dynamics of our two-level system being on resonance with our field. The next step and what we're going to do now, we're going to talk about being off-resonant, what is called the dispersive limit. Okay, so we're still staying within the Jaynes-Cummings approximation, but we're going to allow delta omega c over omega q to be much, much larger than omega naught. Okay, so now we're going to be looking, we'll keep this. Now we're going to be looking at the off-resonant regime. So instead of calling it on resonance and off resonance, I'm going to be calling this, so this is called dispersive. Okay, where omega q minus omega c, which we define as delta, is going to be much larger than omega naught. But the Jaynes-Cummings still holds because omega naught is still small. So we're not going out of this regime yet. And what I'm going to show you in this dispersive limit, what we're going to do is, because we have delta here and we have omega naught, what we're going to do explicitly is we're going to explicitly do perturbation theory. In the small parameter, which is omega naught over delta. And what you will see in this limit is that we can diagonalize this Hamiltonian. What we did on resonance is that we looked at each doublet and we diagonalized each doublet and looked at the dynamics there. And we understood that there is a number conserving, so we looked at the dynamics there. Here what we're doing is we're going to look at the whole spectrum, but because we have this small parameter, we're going to do perturbation theory and take the diagonal elements, which are going to be the largest, in this perturbation theory. Okay, so we're going to, in this term, we're just going to develop the series and throw away the non-diagonal terms, which are going to be much smaller than the diagonal terms, and get a diagonal Hamiltonian and see how that behaves. So that is the plan for this dispersive limit, okay, for what is called the dispersive limit. So we will we'll diagonalize the Hamiltonian in this thing. Oh, I can see that we're out of time. So, okay, so if we're out of time, are there any questions? What we're going to do next week, you can interrupt me if you have questions, but what we're going to do next week, we're going to finish, I wanted to finish this dispersive this week, but didn't get to it. We're going to finish this thing, this dispersive limit, and that will conclude our Jaynes-Cummings Hamiltonian. Then, if I forget this, please remind me. We'll talk a bit about what the seminars will be and what I expect from you in the seminars, since we're about 2 months away from that, and some people were asking about that. So I'll give you the exact format and what are the requirements for that and what materials goes into that. And then we'll start discussing the main systems, which are cavity QED, circuit QED, neutral atoms, and trapped ions. Okay, so you'll have a lesson on each of those. Okay, the atoms and the trapped ions will have guest lectures. I will be the guest lecturer, I guess, on the circuit QED, and I will be the guest lecturer on the cavity QED. Okay, that's it. Okay, all right, so I'll see you next week.